Audio Jungle. Audio Jungle.
In GATE question, they are asking from 2 marks from this chapter, from thin air foil theory. They are asking question that 2 marks to 4 marks, sometimes 2 marks or sometimes 4 marks, 2 questions they will ask to you. It is very important actually, and it's very small chapter only. All right, now, so check. The chapter name is thin airfoil theory. Okay, that weightage of this chapter in GATE is what? 2 to 4 marks. It is very important. Okay, I'm saying GATE. So if you talk about thin airfoil theory, so first very important for this is assumption. Okay, assumption I will tell you, then I will tell you what is the approximation. Okay, first very important is what? Assumption. Okay, assumption. So what are the assumptions? It is valid for 2D flow, inviscid. Okay, incompressible. Okay, irrotational, irrotational. It is valid only for a small angle of attack, AOA. That means small AOA means angle of attack. Okay, small T max by C. Okay, and small Z max by C. These are the assumptions for this thin air fall theory. All right, what is Z max by C? What is T max by C? Will tell you. So it is restricted. Okay, it is restricted for these points. I mean, it is valid for 2D flow. It is valid for inviscid, incompressible, irrotational. Okay, small angle of attack, small T max by T, and small jet max by C. This is the assumption. So maybe they may ask sometimes assumptions in few PSU's exam or in even GATE also. So be aware with this. It is very important. All right. Now we'll go with the very precise thing. What is the mean of the thin air foil theory and what is the approximation of? Okay. Now check. We'll go for, I'll draw one thin airfoil. Okay, this is what thin airfoil. Okay, free stream velocity is main. Now imagine that the airfoil in this figure is made very thin as I have drawn. Okay, I told you generally three types of the airfoil we have: thick airfoil, medium airfoil, and thin airfoil. So I assume that this is a very thin airfoil. Okay, you stand somewhere, stand back, and look at such a thin airfoil from a distance. The portion of vertex sheet on the top and bottom surface of airfoil would almost coincide. What is the mean of it? See, so basically, suppose this is the airfoil, air is what flowing over it. So now you can replace this. This is called approximation of the thin airfoil or thin airfoil approximation. Now, if you stand somewhere and if you check the whatever the vertex sheet you may get on top surface and bottom surface. Okay, top surface and bottom surface. Okay, if you are standing somewhere here and when you are watching for this airfoil, so you may get one approximation. What is the approximation for it? Approximation is very clear because it's a very thin airfoil. So you may get that top and bottom surface, whatever the vertex sit on the top and bottom surface you may get of this thin airfoil, it will almost coincide, and once it will coincide, then it's called the approximation of thin airfoil, and it will be replaced by one single vertex sheet. Okay, and whatever the vertex you may show on the airfoil, it will be because this thin airfoil is what now going to replace in a single vertex sheet. Okay, so but where you will show the vertex, so that will be one camber line. So two things you have: you can show the vertex sheet on camber line, or you can show that vertex sheet on chord line, because camber line and chord line both I have told you. But very good, one thing is very good for the this thin airfoil approximation, because it is very thin, hence your camber line and chord line will overlap to each other, it will coincide to each other. I will show you, it's very simple. So now here this is called thin airfoil approximation. So you have to show one camber line here. Okay, and here we have to show the vertex. Okay, so that vertex will be like this only. I will show you here. Yes or no? Okay, so here this you can say this is what vertex sheet on camber line, and this vertex sheet will be represented by gamma. Gamma, this is the gamma, it will be represented by gamma, and this length itself from this end to this end, it is s. So it is distributed over the length s. Okay, so this is called gamma s. What is the gamma s? Gamma x, sometimes it is noted by this also, gamma x. It is nothing but strength of, it is nothing but strength of vertex sheet. Okay, so hope you understood this approximation. So now this thin airfoil is what can be represented like this. Okay, So because it is very thin, so top and bottom surface, if you stand somewhere, then you may get whatever the vertex over the top and bottom surface, it will coincide to each other, okay, and then it will be approximated, and it will be that airfoil will be replaced by a single vertex sheet distributed over the camber line of the airfoil. This is called thin airfoil approximation. What it is called? In short, I am saying, okay, this is called thin airfoil approximation. Thin airfoil approximation. Okay. Yes or no? Always remember this part. So this distribution of vertex or distribution of vertices, here you can show, as I told you, in two way. Okay, I'll show that, and it is nothing but, see, this is what thin airfoil. This is the coordinate system, I can say. This is nothing but z, and this is nothing but x. Okay, we can call it like this. All right. Now I can show the airfoil. This is the airfoil. Okay. Fine. So this is what airfoil. Yes or no? Now, so is this is straight line. This is what O. So this is straight line from leading edge to trailing edge. What is this? What is this? Leading edge to trailing edge. This straight line will be what? It will be called, yes or no? Chord C. Where will be the cambered line? This will be the cambered line. Okay. This is the cambered line. Okay. So that distance maximum, okay, maximum distance, you can say upper and lower surface. This will be what? T max. And maximum distance between cambered line and chord line called jet max. So now we have both. This is what chord line, and this is what camber line. Is that clear to all? Because it is very thin, okay, because it is very thin, so two options we have. What are the two options? That two options we have, that we can say that thin airfoil, because if it is thin, then you can also call it symmetric airfoil. In thin, both are there, cambered and symmetric, both are there. I'm talking here a symmetric airfoil, okay. So obviously in case of symmetric airfoil, that's the reason this thin airfoil assumption you may take, like chord line and camber line may coincide. If it is coinciding, it becomes a symmetric airfoil. Okay, and for flat plate also the same concept will come into picture, because flat plate also it's symmetric. Okay, So now this vertex sheet you can show on camber line. Vertex sheet you can show on camber line. You can show on chord line. Okay. How you may show it? It's very simple. Okay. So I'm showing vertex sheet on camber line. This is what camber line, check. Okay. This is what camber line. This is the cambered line, and over the cambered line you have to show the vertex sheet. This is the vertex sheet. Vertex here you can show. Okay. So this is what vertex sheet on camber line. What is the magnitude of it? I told you here magnitude is nothing but gamma s. Okay. This is the, you can say this length itself is nothing but c. Okay. Fine. Another is what vertex sheet on chord line. So this is what chord. So if you show vertex sheet on chord line, so this is the cambered line, but you are not going to show the vertex sheet on the cambered line. You are going to show the vertex sheet on chord line. Okay. This is what chord line, and here you are showing the vertex sheet. All right. That magnitude is nothing but. Now you can show the free stream velocity which is coming at alpha angle of attack. So that air, you can show that air here, alpha, it is coming with some angle of attack v infinity. So here also you can show. This is the free stream velocity v infinity now. Okay. And what is the alpha? As I told you, alpha is the angle of attack and you know this thin airfoil theory is what bounded for or restricted for a small angle of attack, bounded or restricted for a small angle of attack. Okay. Now so what is the equation of thin airfoil theory? Okay. So here we have the derivation, but what very good conclusion we got? we got that two component of the velocity. Okay, two component of the velocity. One is w dash, okay, and w dash will be the velocity or component of velocity normal to the camber line, which is induced by the vertex seat, because gamma s you have seen, right? Vertex seat you have seen. So one velocity component will be w dash, and this w dash will be the velocity component normal to the camber line, normal to the camber line. So two velocity component you may have. One will be, you have to show here, which is nothing but normal to the w dash s. This is the w dash, and s is the along the length of camber line. W dash is the velocity normal to the camber line. Okay, similarly if you show this, this is what vertex seat on chord line. So because of this gamma, because we have gamma, okay, and this gamma is what, that is the vertex seat, and it will be the uh, along the chord line. Okay, so you can say this is nothing but gamma c, and because of this gamma c we will get velocity component, which is nothing but w. Okay, w, you can say gamma c, or you can say gamma x, because this length itself x length also, because it's a x coordinate. Okay, if you write c, c means the full length, but suppose it is some partial length, so better to write gamma x. Yes or no? What do you mean by gamma x? Its mean is, its meaning is vertex seat on the chord length, gamma x. Okay, this one. So definitely induced velocity you may get now normal to the chord line. So I can write here w dash s. This is the normal velocity component. What it is this? W dash is the component of velocity normal to the camber line. Similarly, wx, it is the component of velocity normal to chord line, and obviously it is induced by vertex seat, and it is induced by vertex or vertex seat. Okay, both cases. Here also this is also induced by vertex seat, and this is also induced by vertex seat. All right. So two velocity component you may get. One is w dash s, which is the component of velocity normal to the camber line. Second thing, because we are having free stream velocity v infinity, so this v infinity will also have a normal component, which is called v infinity n, and it will be the component of free stream velocity normal to the camber line. Okay, so for camber line, now it's a camber line, it is like now a streamline, because that flow will be tangent to it. Okay, so it will be like a streamline, because you know what is the streamline, that if you draw tangent to the curve, then it will give the velocity of the flow. Okay, so similar kind here I have drawn this v infinity as a tangent to the camber line. Okay, so this camber line will be treated as a streamline. So you know the property of the streamline. What is the normal component over the streamline? It is 0 always. Okay, so I will mention here, it's very simple and need to explain more, but I will suggest not required. Why? Because if you go in very deep uh, like derivation and all, so it will consume the timing. The only thing is I am just explaining the fundamental thing, that's all. Okay, done. Now, so what we have, we can say, let v infinity n be the component of free stream velocity okay, normal to the camber line. Thus, for the camber line, to be streamlined, and you know the property of a streamline, the normal component of velocity normal to the streamline will be velocity component normal to the streamline will be 0. So what we have? We have two normal component of velocity. One is v infinity n, and from where you got this v infinity n? This v infinity n you got component of free stream. You have seen free stream v infinity, I have shown you by the angle alpha. So that will have a normal component, okay, plus one which is called w dash s. What is w dash s? It is the induced velocity by the vertex, and it is normal to the camber, and this sum will be 0. This is very important actually. Okay, now from here you can write the, this is the main equation actually. Now from here you can write the two different velocity component and add and make it equal to 0. You will get the equation of thin airfoil. Yes or no? How to get this v infinity n and w dash s? It's very simple. V infinity n, I will give one diagram better. So from there you can write, you may get it. Okay. Check, this is now chord line, and this is what? Camber line. Okay. You have seen this is the angle of attack alpha, and this is the v infinity n. Okay. Now you know this axis is called x axis and this axis is called z axis. So perpendicular distance here, this is z. Yes or no? It's a z x axis. If I say what is the tan theta, so it's like, so here if it is theta, okay, so this will be what? Dz, and this will be dx. Here this is what? Theta. So what is the tan theta? It is dz by dx. Simple. So basically if I draw the V infinity here, then where is the normal component? Normal component, normal to what? Normal to the chord line. Yes or no? Normal to the chord line. So I'll show how you can find that. It's a simple only. Normal to the chord is what? I must draw like this. This is normal to the normal to the camber, because V infinity is what? Component free stream velocity normal to the camber line. Yes or no? So this is normal to the camber I have drawn. Okay. Now, and this V infinity n is the component of V infinity, and where is the V infinity? V infinity is what? Just parallel to this I can draw here. This and this parallel. This is what? V infinity n. What is this angle? Alpha. Yes or no? So now this is V infinity. Okay. This is making 90-degree. So what is this component? V infinity n, because this is the V infinity, this is V infinity n, and this will be V infinity tangential. Yes or no? So this V infinity is nothing but this one. Okay. So if you calculate this V infinity n, you can use trigonometry. So what you may get V infinity n? V infinity n, what you may get by this diagram only? Directly I am writing this, you can calculate by your own. So what you may get? V infinity, okay, sine alpha plus tan inverse dz by dz. This term will come into picture. Okay, I told you this slope, huh? So for thin airfoil, what will be the alpha? Alpha is small. So for a small angle of attack, sine alpha will be alpha only. Yes or no? Because if you multiply it, then you may get that. And similarly, that tan inverse minus dz by dx will also be small value. So what you may get? You may get V infinity value, V infinity n. You can do that mathematics. You can perform that. V infinity, you may get alpha minus dz by dx. Check this part. This sine alpha, because sine you multiply inside, so sine alpha will be alpha, and tan inverse, you can say that tan inverse sine theta approximate for a small angle of attack, sine theta approximate to tan theta, and it is approximate to theta only. So instead of theta, you may get not tan inverse minus dz by dx, you may get only minus dz by dx. You can do that mathematics, it is simple only. So this is the value of V infinity. How to get the W dash S? That is the another challenging thing. So you can get this. How? This W dash you can get. This W dash you can get. You say like, because it's a thin airfoil, okay, so that camber line will be coinciding to the chord line. So you may get This is x and this is what, z. Okay, so camber line will be coinciding to the chord line here, because it's a thin airfoil. So I can say the coordinate system will be, now this is what, z and x, and you can represent it by zeta, because now chord line and camber line both are coinciding, so I have denoted by one another axis called zeta or xi. Okay, so here you can show the vertex sheet now. So vertex sheet will be like, see, okay, this is the vertex sheet now. Okay, and the velocity component will be perpendicular to this chord line, and it is w. Yes or no? I have taken one small segment, just say this at any distance zeta, one segment I have taken, you just say d zeta or d xi. Okay, fine. Now if you want to calculate what is the induced velocity at the distance of x, okay, so you can write here the induced velocity at point x. I can say this is nothing but x. Okay, induced velocity at x due to due to elemental vertex at point zeta is given by, so that induced velocity will be dw, which is nothing but gamma zeta into d zeta divided by 2 pi x minus zeta. Okay, at trailing edge what will be zeta? 0. At zeta started from leading, this is the leading edge, sorry, and this is somewhere you just say trailing edge for the, so for leading is le, at leading edge zeta will be 0, at trailing edge zeta will be c. Yes or no? Chord length. So what will be the limit here? What will be the limit if you put, then your wx you may say, then it will be minus, this is minus sign because that induced velocity will be going downward, so hence you will take minus. If it is going upward, then you will take positive. Okay, so minus 0 to c, it is nothing but gamma zeta d zeta 2 pi. All right, this is the wf. So what is your equation of thin airfoil theory? It is nothing but You know that. What is that? V infinity n plus w dash x. Now this is also because your chord line and camber line coinciding, so it will be same, equal to 0. What is V infinity? You got V infinity n. Check, it is nothing but V infinity in bracket alpha minus dz by dx. Okay, and this is nothing but w dash x. Just now you have achieved, it is nothing but 1 upon 2 pi 0 to c gamma divided by 2 pi. This equation is nothing but called, this is the governing or fundamental equation of thin airfoil theory. Okay, this is the fundamental equation. Fundamental equation of thin airfoil. So this is valid for all. I mean, it is camber airfoil or it is symmetric airfoil for flat plate, for anything. Now you can derive from here. If it is flat or if it is like flat, you can say flat plate, then dz by dx will be 0. What is the assumption you have taken here? You have made assumption in your statement that the camber line is a streamline of the flow, and then you proceeded it, because then only you may get. Okay, here you have taken that. What was the statement? You have made the statement camber line in single marks they can ask to you. Okay, so camber line is a streamline of the flow, then only this part will be 0. Streamline of the, then only normal component to the streamline will be 0, right? So this is what, this is the equation of streamline. Okay, now this equation of not equation of streamline, this is the characteristics of the streamline, that normal component or normal velocity to the streamline will be 0. Okay, and you have used that characteristics, and then finally you got the fundamental equation of thin airfoil. Now from here we can derive the required thing. Okay, so like in next class we'll derive all the parameters. Okay, all right, done.